X-Ray Magnetic Circular Dichroism. Short name is Xmcd. During the last lecture, we have discussed X-ray resonant magnetic scattering, XRMS. If you understand the XRMS method, you can easily understand this method. So what are the advantages of this method? This method is element specific. What we mean with element specific, we have already discussed this one in XRMS lecture. If you have a multi-layer system, for example, iron, cobalt, nickel layers in your multi-layered sample, then you can investigate each layer element specifically. You can investigate the magnetic properties of each material, okay? In addition to that, if you have an alloy, for example, coffee B, cobalt, iron, boron, then you can investigate each element within the single layer element specifically. So you can investigate the magnetization of the cobalt, magnetization of the iron, and you can also investigate boron specifically. So this is the unique property of the Xmcd and XRMS methods. In addition to that, spin and orbital moments can be determined separately in case of Xmcd experiments. So what we mean in atoms, electron is traveling around nuclei, right? And during this orbital motion, electron has an orbital magnetic moment, okay? In addition to that, electron has a spin magnetic moment. So in magnetic materials, especially in ferromagnetic materials, what I mean iron, cobalt, nickel, for example, the magnetization of the system, magnetization of the atom, magnetization of the material mainly comes from the spin contribution, okay? Orbital contribution to the magnetization is usually neglected in ferromagnetic materials, but sometimes it is also important to know this information. So by using Xmcd, you can separately determine spin and orbital magnetic moments of elements. In addition to that, this method is used by changing the polarization of the incident photon from the synchrotron light source. You choose the incoming polarization of the photon, and then you carry out your measurement and you change the polarization and you repeat your measurement. So in case of Xmcd experiments, we change the polarization of the incident photon. So we mainly use circularly polarized light. But in case of XMLD, there is another method, X-ray magnetic linear dichroism. In case of XMLD, linear polarization is also used, and no magnetic field is applied to the sample during the measurements because Xmcd experiments are affected by the magnetic field. It is related to the experimental design. I will go into detail in the forthcoming part of my lecture. And this method is difficult to measure because you have to prepare very nice, very thin samples, especially in transmission method. I will go into detail. But also for other methods, there are also total electron yield method, fluorescence yield method. And in case of these methods, you have to prepare very nice surface of the sample. Okay, this method is surface sensitive. I will go into detail. For this reason, you have to prepare very good samples. In addition to that, the beamline optics must be perfect, okay, in order to carry out these experiments. Now let me continue with the Xmcd measurement setup. We have discussed this setup in XRMS lecture. This is the same setup and located in Gebze 2 in Berlin. And this is the beamline. X-ray is coming from the beamline, and this is the sample holder. Here we have detector, here we have magnet poles. You can apply magnetic field. And we have a temperature controller system, and we have liquid helium flow cryostat. Then you can cool the sample down to 4.2 Kelvin, and you can heat the sample up to 475 Kelvin. So you can carry out this Xmcd experiments at different temperature conditions. In addition to that, you can change the direction of the magnetic field. You can change the magnitude of the magnetic field. So you can manipulate the magnetic field within this range. minus plus 2700 Ørsted. So this is the experimental chamber which is used for XRMS and XMCD experiments. And what about the basics of XMCD experiments? What is the origin of this physical phenomena? Here I will try to explain the mechanism. In order to understand the XMCD method, you have to understand two-step model here. Before we start for two-step model, just look at the energy levels of electrons in a ferromagnetic material. Let's say here on the left side, we have a figure. This is the 3D band structure of the 3D elements. Let's consider iron, cobalt, nickel, chromium, manganese, for example. Okay, so what we have here, we have 2p3½ electrons in this level and 2p1½ electrons in this level. So we have spin up electrons and also spin down electrons. This is just representation, okay? And here we have spin up electron and spin down electron. So in total, in the 2p level, we have 6 electrons. And here in the 3D level, we should have actually 10 electrons if it is completely full. But in case of iron, cobalt, nickel atoms, we have some unoccupied levels in the 3D level. Okay, for example, for the iron, as much as I remember, we have 6 electrons, and for the cobalt, 7 electrons, and also for the nickel, 8 electrons, as much as I remember. Then we have some unoccupied 3D levels. So what do you see here? We have spin up electrons in the 3D level and also spin down electrons in the 3D level. So here, above the Fermi level, what do you see? We have some unoccupied levels. So then what about the two-step model? In two-step model, this 2p3½ and 2p1½ levels or shells are viewed as spin polarized sources. So what we mean with spin polarized sources, here we have spin up electrons and spin down electrons in the 2p levels, okay? So these are the electrons. And these levels are considered as source of electrons, okay? And what about the 3D level? The vacant spin up and spin down 3D bands are viewed as spin sensitive detectors. Here we have source, electron source. Here we have electron detector, let's say, okay? You can consider like this. And how to use this 2p3½ and 2p1½ levels as spin polarized sources. Here we have circularly polarized light, X-ray, okay? And this circularly polarized light has energy around the binding energies of electrons in these levels, okay? You remember from the XRMS lecture, the binding energies of the electrons depend on the element, okay? So you choose some certain energy for the incoming circularly polarized light, and then you send these photons to your material. If this incoming photon energy is around the absorption energies of this L3, L2 levels, then you can excite these electrons from these levels. Then you can excite them to the upper energy levels. You can excite them to the 3D level, okay? So then these 2p levels are considered as spin polarized source. And here we have some unoccupied levels, some empty levels in the 3D band structure, okay? And for example, here you excite from this level spin up electrons, but we have less place here for them. But if you excite spin down electrons, we have more place for spin down electrons. So this level, this 3D level, works as detector, spin sensitive detector Okay, you can consider like this, source and detector. So this is the two-step model. First of all, you excite electrons from the 2p levels, and then you detect them in the 3D levels. Okay, here we have a term spin polarized. Spin polarized means that you send electrons with some certain spins. Okay, so all of them have spin up, and here all of them have spin down. Okay, so each electron has spin up here, and each electron has spin down here. So then we have spin polarized electrons. Okay, you can consider like this. But what happens if you send circularly polarized light to the 2p level of the elements? If you send circularly polarized light to the L3 edge, this level, so you select the incoming photon energy. You can do this one with the monochrometer in the beamline. You select this energy, so this level has certain energy depending on the element, and then you send circularly polarized light. So if you send right circularly polarized light, then this photon excites 62.5% spin down and 37.5% spin up electrons. So you can excite less spin up electrons and more spin down electrons from the L3 edge if you use right circularly polarized light. We have discussed the polarization during the last lecture. What is the right circularly polarized light? What is the left circularly polarized light? You can check the lecture notes which we have discussed during the last lecture. And if you send left circularly polarized light to the same level with the same energy, then this photon does the opposite. So what I mean, you mostly excite spin up electrons 62.5%, and then you excite 37.5% spin down electrons. It is vice versa. So right circularly polarized light and left circularly polarized light do the opposite jobs. Okay, in case of L2 edge, if you send X-rays with energies close to the L2 edge of this element, if you send right circularly polarized light, then this photon excites 25% spin down. So you excite 25% spin down to the 3D level, and you excite 75% spin up electrons if you use right circularly polarized light. But if you use left circularly polarized light, you excite 25% spin up electrons and you excite 75% spin down electrons. So this does the opposite. Okay, so depending on the incoming photon energy, depending on the incoming photon polarization, you excite different spin up and spin down electrons from the 2p levels. Okay, this is the first stage of the two-step model. Now let's discuss the second step. Second step, detection of this excited electrons. So I have already discussed, if you have enough place for the excited electrons, then they can come here. But let's consider that this level is completely filled. Okay, I mean, let me draw another band structure for the 3D level. So let's consider that 3D level is like this. This is spin up, spin down configuration, and there is no place for the spin up electrons. Then you excite spin up electrons from these levels, from 2p levels, but there is no place for them. So then this part of the band structure works like spin sensitive detector. Depending on the incoming spin, there is a place or not, okay? So this level behaves like spin-sensitive detector. So this is called as two-step model. The first step, excitation of electrons, depending on different polarization and energies, you excite spin-polarized electrons, and then here you deal with the detection of the electrons. Now let's come to the right side. Here on the right side, we have a real Xmcd data. Okay, this is taken from the iron. What we have here, this is the photon energy in the x-axis, and here we have the X-ray intensity read by the detector. So what do you see here? Photon energy. Look at this one. These are the L3 and L2 energies for the iron. Okay, remember the last lecture, binding energies for the iron electrons in 2p3½ and 2p1½ levels. So why we have this kind of shape? Why we see peak here and why we see peak here, and why we have different colors here in this picture? Now I will try to explain this one. If you understand this one, you will also understand the mechanism of the X-ray resonant magnetic scattering, which we have discussed during the last week. So let me start with the blue one. What is this blue one? Let's consider you use RCP, and I will show you the LCP with different color. We are using right circularly polarized light. So then we are working at this energy. You are changing the energy of the incoming photon by using the monochromator in the beamline, and you use right circularly polarized light. So what we have learned that around the L3 edge, RCP photon excites 62% spin down and 37.5% spin up. And we have this intensity. What we mean with the intensity, you read the intensity at the detector. I will explain different methods used in Xmcd, but now just try to understand the mechanism. And here you continue to scan the energy. Just look at the figure here. We scan the energy. We have started before the 700 electron volt, and we continue to change the energy of the incoming photon. And now energy is close to the L2 energy of the iron element. And if you have sent photons with the energies around L2 edge, then right circularly polarized light will excite 25% spin down and 75% spin up. So what do you see here? It is opposite, okay? So then we see here this type of curve. Around the L3 edge, absorption occurs and we have intensity. And around the L2 edge, absorption occurs and we see intensity. And far from the L2 edge and before the L3 edge, you cannot see any absorption, okay? Because the incoming photon energy cannot excite electrons because the energy is far from the energies of this absorption edges. In order to understand the behavior of this figure, you have to understand the two-step model. Two-step model tells us this L2 and L3 energies can be considered as spin-polarized sources, and this 3D level can be considered as spin-sensitive detector, okay? So depending on the polarization, you excite different electrons from this L2, L3 energies, and depending on the spin up and spin down configuration of the electrons, we have enough place in the 3D level or not, okay? So depending on this configuration, you get this type of picture, this type of result from the 3D elements. So now let me discuss another element in the 3D level. For example, just consider copper, 3D10, okay? What it means, the 3D level is completely filled. And here there are 2p levels, okay? Spin up and spin down electrons. Since there is no difference between the spin up and spin down electrons for the 3D level, so the 3D level cannot work as a detector. Then what you will see in case of the copper, let me clean this part and try to draw the Xmcd result for the copper. Let's consider this is the photon energy, electron volt, just as for the iron. And here we have the intensity, and you scan the energy. Then here we have an absorption, and here we have another absorption. Just consider L3 and L2 for the copper. And let's consider this is for right circularly polarized light. Then change the polarization, left circularly polarized light, and you will measure exactly the same curve. There will be no difference in between. In case of iron, you can see huge difference between the intensities depending on the incoming photon polarization, but for the non-magnetic copper, you cannot see any difference because spin-sensitive detector does not work, okay? The 3D level is completely filled in case of copper, okay? So then you cannot see any difference. I hope now it is clear. Then let me continue with the Xmcd measurement setup and different methods used in Xmcd experiments. Let me start with the total electron yield. This is mostly used method, total electron yield. Actually, Xmcd experiments are the absorption experiments. Remember the X-ray matter interaction in the second chapter of this lecture. What we have learned in absorption experiments, we have three absorption products: photoelectrons, Auger electrons, and fluorescence X-rays, right? These are the absorption products. So when you send synchrotron radiation into your sample, you can produce these three absorption products: electrons, photoelectrons, Auger electrons, and also fluorescence X-rays. So each absorption product can be used in Xmcd experiments as a different method. In case of total electron yield, we consider that we count photoelectrons and Auger electrons coming from the surface, coming from the material. This is the magnetic material, thin film. This is the synchrotron light source, comes with some certain angle, okay? And this is the direction of the magnetization. And when synchrotron light, X-rays, interact with the atoms, electrons of this material here, then we produce many photoelectrons, many Auger electrons, and these photoelectrons, Auger electrons are distributed everywhere, okay, within the material. And some portion of these electrons can reach to the surface of the material, okay? And if you make a contact on the surface of the material, then you can measure the current, and it is proportional to the absorption happens within the material, okay? So X-ray is coming to the L3 and L2 edges of this element, okay, with some certain energy, and then this electron is excited, you produce photoelectrons. You can also produce Auger electrons. Of course, mostly photoelectrons. Remember that more than 95%, which we have discussed this one in the absorption experiments part. And then we have many electrons on the surface. And if you make a contact on the surface, then you can count them, okay? You can measure the current. Then, depending on the incoming photon polarization, right circularly polarized light or left circularly polarized light, So you can get different results in Xmcd experiments for the TAY method. This is called as TAY method. Okay, you measure the electrons. Okay, so this is total electron yield method. And we have another method, fluorescence yield.
For example, in this sample, you are writing that capital M like it's magnetization, but
Yes.
you say you are not using magnetic field.
Okay, but this is not the magnetic field. This is magnetization of the sample, internal property of the sample. Is it clear?
Yes, yes.
I am not using the magnetic field source, okay? There is no magnetic field. Actually, magnetic field is used with H symbol, okay? Or with B symbol. This is magnetic field. This is magnetic flux density or magnetic induction, okay? So in order to show the magnetic field, B or H symbols are used. And in vacuum, B is equal to H, okay? So this is the magnetic field. And here I don't use magnetic field. What is M? This is the internal property of the material. It is magnetization of the material. But I'm happy with your question. At the beginning of my talk, what I have told you, during the Xmcd experiments, we don't use magnetic field source because the experiments can be affected by the magnetic field, okay? Then let me explain this one, the effect of the magnetic field for this total electron yield. So what we have here in total electron yield, we are electrons on the surface of the material, many electrons. Okay? Just consider that you are doing this experiment like this. Here we have considered that you use right circularly polarized light and you use left circularly polarized light and you repeat the energy scan. But just consider that you use right circularly polarized light and you change the direction of the magnetic field. So you carry out experiments under magnetic field. You keep the polarization, change the magnetic field. In XRMS experiments, we did like this. So what will happen if you apply magnetic field? Just put here a magnet pole and then you apply magnetic field in this direction, let's say. Okay, here we have electrons. Electrons are charged particles. Then here I have magnetic field. Then remember the Lorentz force. Okay, we have charged particles, electrons, they have certain velocity. I have applied magnetic field. Then there will be Lorentz force acting on the electrons and the electron trajectories will be deflected. And if you change the direction of the magnetic field, then just consider that you reverse the direction of the magnetic field and then you change the direction of the Lorentz force and you will affect your experiment, okay? You will affect your result. For this reason, in Xmcd experiments, in total electron yield method, magnetic field is not used. What we do, before the experiment, you apply the magnetic field and you align your magnetization in some certain direction, and then you remove the magnetic field, then you continue to your experiment. Okay, this is the mechanism. Is it clear, Nora?
Yes, clear, thanks.
Okay, so now let me continue with the fluorescence yield. In case of fluorescence yield, actually here in this method, in the total electron yield method, we are dealing with the electrons, but we have also many fluorescence X-rays, okay, but we don't care them. But in case of fluorescence yield method, we don't care the electrons, okay. Here we have an incident photon, X-ray comes on the surface, absorption occurs, okay. We have many electrons, but we have also fluorescence X-rays, okay, coming from the material, and we don't care the electrons. We are only dealing with the fluorescence X-rays. Here I put a fluorescence detector, okay, an X-ray detector. Then I count the fluorescence X-rays coming from the sample, okay? Then I measure the same result, okay? So just consider here you have the same iron material, and here you have the same iron material, and in this case you are using the TAY method, and in this case you are using the fluorescence yield. You have to get the same result from the same material under the same conditions. You have to get the same result, okay? It is independent from the method, but usually TAY method is preferred, okay? In the past, I have used both of them. I have did experiments with TAY method, and I have also done experiments with fluorescence yield. But my impression is that with the TAY method, you can get better resolution. So now what about the magnetic field effect in case of fluorescence yield method? Let me discuss also this one here. Let's consider here you have a magnet source. Let's consider this is the magnet pole. This is another magnet pole, and you apply magnetic field. So here we have fluorescence X-rays. X-rays are not affected by the magnetic field because X-rays are photons, and photons have no charge, okay? So Lorentz force cannot do something. In order to apply Lorentz force, a charge is required, okay? X-rays, fluorescence X-rays or other photons have no charge. Then there will be no effect of this magnetic field. But what about the detector? In fluorescence yield method, detector is very close to the surface of the sample, okay? Then remember the detector working mechanism. Gas ionization chambers, scintillation counters, CCD detectors, semiconducting detectors, okay? We have learned many types of detectors, and in each type of detector, what we do, we convert X-rays to the current, right? We convert X-rays to the electrons and current. If you apply magnetic field, then you can affect the working conditions of the detectors, okay? So your detector can be affected by the magnetic field. For this reason, during the measurements, we don't apply magnetic field. Before the measurement, you apply magnetic field, you align your magnetization within the sample, then you remove the magnetic field, and then continue to your experiment, okay? This is the effect of magnetic field in fluorescence yield method. Now, let me discuss the transmission method. This is the last method used in Xmcd experiments, transmission method. So you can understand from the name, here we have the I0, initial photon intensity, and here we have a magnetic field. This is the direction of the magnetization. And this is the thickness of the material, okay? Then this is the final intensity. And here we have a detector, and you record the intensity. This is the photon energy in the x-axis, and here we have the photon intensity recorded by the detector. So what do you see here? This final intensity passing through the sample depends on the initial intensity, and it depends on the absorption coefficient of the material, and it depends on the thickness. We have discussed this one in the second lecture. And this absorption coefficient depends on the beta and also depends on the lambda, energy of the incoming photons or wavelength of the incoming photons. So this is the L3 energy of some element, and this is the L2 energy for the same element, and we scan the photon energy, okay? So what do you see here? Around the L3 and L2 energies, photon intensity drops. You see, intensity drops here. Why? Because if the incoming photon energy is close to the L3 and L2 energies of this material here, then absorption will happen. Okay, then the incoming X-rays will be absorbed. They will be converted to the photoelectrons or J electrons and fluorescence X-rays, and then the transmitted light will have less intensity, okay, when the energy is close to the absorption energies. This is the transmission method. And what about the magnetic field in transmission method? Actually, in transmission method, you are using the transmitted photons, and photons are not affected by the magnetic field, okay? And you can put the detector far from the sample. Then you can also prevent the detector from the effect of the magnetic field. But how to put magnetic field source here? You have to put magnetic field source here like this, okay? If you would like to produce this kind of magnetization in the sample, then, so how to get the photons? So you have to produce a hole within the magnet pole, then X-ray can travel within this hole and reach to the detector. So experimentally, this is also somehow tricky, okay? So actually, the experiment is not affected from the magnetic field. If the detector is far from the sample, far from the magnetic field source, your experiment cannot be affected due to the magnetic field. But, I mean, to prepare these conditions is not so easy. And another important thing here in transmission experiments, look at the material. We are talking about thickness. This thickness is very small. We are talking about few microns, okay? Otherwise, X-rays cannot pass through this material if this is thicker. Then you have to prepare very thin samples for this transmission method, okay? This fluorescence yield experiments and total electron yield experiments can be done by using very thick samples. It doesn't matter because you measure the data from the surface, okay? But in case of transmission, you have to prepare very thin samples, and it is not so easy. You use some chemical methods to get very thin layer of your material, or focused ion beam method is used, okay? Then you produce a cross-sectional part of your material, which is also very thin. Then you can use this one in also Xmcd experiments in transmission method, but this method is usually not preferred, and this total electron yield method is mostly used. Here, I would like to tell you something else. This Xmcd is surface sensitive method, okay? I will explain why. I'm talking about more or less 5 nanometer, okay? So you can get information from this 5 nanometer close to the surface, okay, more or less. Why 5 nanometer? Why this method is surface sensitive? Actually, this incoming synchrotron light source X-rays can penetrate deep into the material, okay? But this absorption products, photoelectrons or J electrons, fluorescence X-rays produced after X-ray matter interaction, for example, this synchrotron light source can reach to this part of the material, and here many photoelectrons, fluorescence X-rays, and Auger electrons are produced, but they cannot reach to the surface. During the traveling within the material, fluorescence X-rays and electrons lose their energies, okay? They cannot reach to the surface. Only the absorption products close to the surface of the material can reach to the surface, okay? Then this method is surface sensitive. Also here, fluorescence X-rays case, okay? Xmcd is a surface sensitive method. So now let me continue with the real Xmcd measurements, how to carry out these experiments and what are the results. First of all, if you are using a diffractometer, you can carry out a sample alignment. Some X-ray magnetic circular dichroism setups do not include a diffractometer. Then they define some certain incident theta angle, and then they continue. But in case of this experimental setup, which we have also used this one for XRMS experiments, we have diffractometer, then you can carry out sample alignment. We have explained the sample alignment steps in the X-ray reflectivity method. You can check them. And then the most suitable angle of incident is chosen after the sample alignment, and the temperature is fixed. This is very important. Even very small fluctuations in the temperature can affect your result because magnetization depends on the temperature. Ferromagnetic materials, especially close to the transition temperatures, magnetization is affected a lot, and also the experimental conditions, I mean, the X-ray matter interaction is also affected with the temperature, so you have to fix the temperature. Polarization is selected, and then depending on the element to be examined, a certain energy range is scanned. As I told you here, okay, we scan the energy. And then the same energy region is rescanned by changing the polarization, as I have explained in the previous transparencies. So what about the electron binding energies? I have discussed this part in XRMS method. Okay, here we have L2, L3 energies of the elements. For the oxygen, during the last lecture, I have shown you we use oxygen KH. So usually we are dealing with magnetic materials in the periodic table, iron, cobalt, nickel. And you see here the energy range for the iron, for the L2, L3 energies, and these are the energies for the cobalt. These are the energies for the nickel. As we have discussed in the XRMS method, these energies are element specific, okay? Depending on the element, you have different binding energies, and it goes for copper and zinc also. So now let me show you some absorption measurements of 3D metals. What do you see here? We have iron, we have cobalt, we have nickel, we have copper here. So you can see this L3 and L2 peaks for the iron, for the cobalt, for the nickel, and for the copper. Why we don't see something for the copper? Because as I have explained, copper is not magnetic, zinc is not magnetic, okay? They are non-magnetic because they have 10 electrons in the 3D level. And what do you see here? That look at the energies, L3, L2 energies for the iron, okay, around these energies. And look at the cobalt around these energies. So they never overlap, okay? They never overlap. If you continue with other elements, you will see absorption energies here. If you continue with the previous elements, you will see absorption energies on the left side at lower energies. Okay, so then this method is element specific. So within the multi-layered systems, you can study each layer element specifically. Within the alloys, you can study each element within the alloy. Okay. So now let me discuss the analysis of Xmcd data, which is called as some rules. Okay, at the beginning of my talk, I have told you that by using the Xmcd method, we can determine the spin and orbital magnetic moments of the elements separately. We have discussed in the first transparency. So how to determine spin and orbital magnetic moments separately? Here I will show you. Just consider that you are investigating iron and you have used right circularly polarized light. and you have used left circularly polarized light, and then you have recorded this data. What do you see here? This blue one, let's consider taken with right circularly polarized light. This red one is taken with left circularly polarized light. Let's say this is the photon energy, same energy range, and this is the intensity read by detector. So here we have two data, okay? This is, you can call it I plus intensity plus taken for this polarization. This is I minus intensity taken for this polarization. So if you plot these intensities in this form, this gives us XAS. What is XAS? X-ray absorption spectroscopy, okay? So then you have this type of behavior. Here we have the same energy range in the x-axis, okay? And this is the XAS data. And the area under this curve is called as C, okay? The area under this curve. And if you plot these intensities in this form, I minus minus I plus over sum of the intensities, then you will get the Xmcd, X-ray Magnetic Circular Dichroism. Then you will get this kind of data. You take the difference in case of Xmcd. So here we have two areas. One is A, the other one is B, and we have here another area which is coming from the XAS. The name is C. So by using this A, B, C areas, you can calculate the spin and orbital magnetic moments. Okay, here we have spin magnetic moment. How to calculate this one, which is given with this equation. You can see the details here in this article. -2 A minus 2B. A is the area here. B is the area here over C. C is the total area in the XAS. Put them here. And here we have 10 minus N3D. What is N3D? Number of electrons in the 3D level. And this depends on the element. And here we have mu Bohr magneton. This is constant. And how to calculate orbital magnetic moments? -4/3 A plus B minus C times 10 minus N3D times Bohr magneton. So what about the N3D? For example, for the iron, we have 6 electrons in the 3D level. For the cobalt, we have 7 electrons in the 3D level. For the nickel, we have 8 electrons in the 3D level. For the copper, we have 10 electrons in the 3D level. So just consider copper. It has 10 electrons in the 3D level. Just put here 10, then it will be 0. Just put here 10, it will be 0. For this reason, you cannot see any feature in the copper, okay? I have also discussed this one in my previous transparencies. So then, depending on the element, depending on the number of 3D electrons, you put the required information here, and you put the areas which you have calculated here. Then you can calculate spin and orbital magnetic moments separately. Okay, this is called as sum rules. Okay, so here you see minus sign. Actually, the result will be positive because look at the A here. A is negative. Look at the B. B is positive. And here in front of B, we have negative times negative, then you will have positive. Look at this one here. A is negative, B is positive, but A is bigger than B, then this will give us a negative number. And here we have a negative sign, then the result will be positive. Okay, so these are the sum rules and the analysis of Xmcd data. And with this transparency, I will finish my lecture. So by using the Xmcd data, you can investigate the spin and orbital magnetic moments separately. You can investigate the multi-layers and those alloys and the elements within these structures, elements specifically. You can investigate the magnetic properties of the materials. But by using these methods, by using the TAY method, fluorescence yield method, by using the transmission method, you can also carry out X-ray absorption spectroscopy experiments, and you can get the structural data of the material. Okay, you can get the information about the structure of the material. Okay, so by using the same method, you can get information about the magnetic properties of the material, but by using the X-ray absorption spectroscopy, you can also get information about the structural properties of the material. Here, I will show you a real example. In the inset here, we have a smaller figure. This is taken from the literature published by Regan and co-workers in Physical Review B in 2001, just more or less 20 years ago. Okay, and here we have data from my PhD thesis taken in 2008. Okay, so now I will discuss again the zinc cobalt oxide aluminum oxide system. Aluminum oxide is the substrate, and we have cobalt ions implanted into the zinc oxide layer. Then we have zinc cobalt material here, okay, with some certain concentration of the cobalt. And then I would like to check whether cobalt sits on the lattice and make bonding with oxygen, or we have cobalt clusters and they behave like ghettos within the material. So this method can give us some information. So here in the inset figure, in the small figure, you see different experiments. Look at this one. These experiments carried out around the cobalt L3 and L2 energy scan, you see. But here we have different cobalt, including materials. This dashed line, you see the first one, dashed line, shows us cobalt oxide. This one. This dashed line shows us the cobalt oxide, the data from the cobalt oxide. And here we have a solid line which includes data from cobalt oxide on iron. This solid black line comes from the cobalt oxide on iron. And here we have black dashed line, which is the simulation result fit, okay, this one fit to the cobalt oxide iron data. Okay, you see this is the fit. And here the last one, this is the solid line, comes from the cobalt metal. Okay, this one comes from the cobalt metal. What is the meaning of cobalt metal? It does not contain oxygen. And here we have cobalt oxide. You can consider that oxidized cobalt fit for the oxidized cobalt, and non-oxidized cobalt. This is pure cobalt metal. What do you see here? If the cobalt is oxidized, you see some features around the cobalt L3 energy. You see there are some fine structures, there are some features around the L3 edge. But if you are dealing with the pure cobalt without oxidization, you see a peak, okay, without any structure. This is more or less sharp peak, okay? There is no feature. So it means that if cobalt is metallic, if it is not oxidized, then you will see sharp peak. If it is oxidized, you will see some fine structure around the cobalt L3 energy. Then you can understand whether your cobalt is oxidized or not. Okay, this is the data from the literature, and this is our experiment. So I would like to investigate the cobalt element within this zinc cobalt oxide, whether it is pure cobalt metallic clusters are present within the material, or cobalt sits on the zinc oxide lattice and makes bonding with oxygen, and we have cobalt oxide within the sample. I don't know this one at the beginning. I would like to check it. Then I am scanning the energy around the cobalt L2, L3 energies. Temperature is fixed. I am using right circularly polarized light and left circularly polarized light, and then I plot the data like this. This is the XAS data, which I have shown you here, okay? Then what do you see here? I have fine structure here, multiple structure here, fine structure here, okay? So this is not the behavior of the pure metallic cobalt. This is the behavior of the oxidized cobalt. Then I can tell you that this cobalt located within the zinc oxide lattice and sits on the zinc side in the lattice and makes bonding with oxygen. So just by this experiment, I can tell you. So this method is very powerful, element specific, and depending on the element, depending on the layers, you can get element specific information, layer specific information. And in addition to that, you can get the data from spin and orbital magnetic moments of elements separately. So with this one, I finished my lecture. Next week, we will continue with X-ray imaging methods by using X-rays. Take care of yourself. Bye-bye.